Our process. In nuclear astrophysics, the rapid neutron capture process, also known as the OR process, is a set of nuclear reactions that is responsible for the creation of approximately half of the atomic nuclei heavier than iron, the heavy elements, with the other half produced by the P process and S process. The OR process usually synthesizes the most neutron-rich stable isotopes of each heavy element. The OR process can typically synthesize the heaviest 4 isotopes of every heavy element, and the 2 heaviest isotopes, which are referred to as our only nuclei, can be created via the OR process only. Abundance peaks for the OR process occur near mass numbers at equals 82 elements CBr and Kr, at equals 130 elements T, I, and Z, and at equals 196 elements OS, or in PT. The OR process entails a succession of rapid neutron captures, hence the name, by one or more heavy seed nuclei, typically beginning with nuclei in the abundance peak centered on 56 phi. The captures must be rapid in the sense that the nuclei must not have time to undergo radioactive decay, typically via B decay, before another neutron arrives to be captured. This sequence can continue up to the limit of stability of the increasingly neutron-rich nuclei, the neutron-drip line, to physically retain neutrons as governed by the short-range nuclear force. The OR process therefore must occur in locations where there exists a high density of free neutrons. Early studies theorized that 1024 free neutrons per cm3 would be required for temperatures about 1 GK in order to match the waiting points at which no more neutrons can be captured, with the atomic numbers of the abundance peaks for a process nuclei. This amounts to almost a gram of free neutrons in every cubic centimeter, an astonishing number requiring extreme locations. Traditionally, this suggested the material ejected from the reexpanded core of a core collapse supernova as part of supernova nucleosynthesis or decompression of neutron-star matter thrown off via binary neutron-star merger. The relative contribution of each of these sources to the astrophysical abundance of our process elements is a matter of ongoing research. A limited OR process-like series of neutron captures occurs to a minor extent in thermonuclear weapon explosions. These led to the discovery of the elements einsteinium element 99 and fermium element 100 in nuclear weapon fallout. The OR process contrasts with the S process, the other predominant mechanism for the production of heavy elements, which is nucleosynthesis by means of slow captures of neutrons. The S process primarily occurs within ordinary stars, particularly AGB stars, where the neutron flux is sufficient to cause neutron captures to recur every 10-100 years, much too slow for the OR process, which requires 100 captures per second. The S process is secondary, meaning that it requires pre-existing heavy isotopes as seed nuclei to be converted into other heavy nuclei by a slow sequence of captures of free neutrons. The OR process scenarios create their own seed nuclei, so they might proceed in massive stars that contain no heavy seed nuclei. Taken together, the R and S processes account for almost the entire abundance of chemical elements heavier than iron. The historical challenge has been to locate physical settings appropriate for their timescales. History. Nuclear physics. There are 3 candidate sites for a process nucleosynthesis where the required conditions are thought to exist: low-mass supernovae, type Roman II supernovae, and neutron-star mergers. Immediately after the severe compression of electrons in a type Roman II supernova, beta- decay is blocked. This is because the high electron density fills all available free electron states up to a Fermi energy which is greater than the energy of nuclear beta decay. However, nuclear capture of those free electrons still occurs and causes increasing neutronization of matter. This results in an extremely high density of free neutrons which cannot decay, on the order of 1024 neutrons per cm3, and high temperatures. As this re-expands and cools, neutron capture by still existing heavy nuclei occurs much faster than beta- decay. As a consequence, the OR process runs up along the neutron drip line and highly unstable neutron-rich nuclei are created. Three processes which affect the climbing of the neutron drip line are a notable decrease in the neutron capture cross-section in nuclei with closed neutron shells, the inhibiting process of photodisintegration, and the degree of nuclear stability in the heavy isotope region. Neutron captures in our process nucleosynthesis leads to the formation of neutron-rich, weakly bound nuclei with neutron separation energies as low as 2 MeV. At this stage, closed neutron shells at n equals 50, 82, and 126 are reached, and neutron capture is temporarily paused. These so-called waiting points are characterized by increased binding energy relative to heavier isotopes, leading to low neutron capture cross-sections and a buildup of semi-magic nuclei that are more stable toward beta decay. In addition, nuclei beyond the shell closures are susceptible to quicker beta decay owing to their proximity to the drip line. For these nuclei, beta decay occurs before further neutron capture. Waiting point nuclei are then allowed to beta decay towards stability before further neutron capture can occur, resulting in a slowdown or freeze out of the reaction. Decreasing nuclear stability terminates the OR process when its heaviest nuclei become unstable to spontaneous fission, when the total number of nucleons approaches 270. The fission barrier may be low enough before 270 such that neutron capture might induce fission instead of continuing up the neutron drip line. After the neutron flux decreases, these highly unstable radioactive nuclei undergo a rapid succession of beta decays until they reach more stable, neutron-rich nuclei. While the S process creates an abundance of stable nuclei having closed neutron shells, the R process, in neutron-rich predecessor nuclei, creates an abundance of radioactive nuclei about 10 AMU below the S process peaks after their decay back to stability. The R process also occurs in thermonuclear weapons and was responsible for the initial discovery of neutron-rich almost stable isotopes of actinides like plutonium-244 and the new elements einsteinium and fermium atomic numbers 99 and 1. It has been suggested that multiple nuclear explosions would make it possible to reach the island of stability, as the affected nuclides, starting with uranium-238 as seed nuclei, would not have time to beta decay all the way to the quickly spontaneously fissioning nuclides at the line of beta stability before absorbing Mo, thus providing a chance to reach neutron. Astrophysical sites. The most probable candidate site for the OR process has long been suggested to be core collapse supernovae spectral types IB, IPE, and Roman II, which may provide the necessary physical conditions for the OR process. However, the very low abundance of our process nuclei in the interstellar gas limits the amount each can have ejected. It requires either that only a small fraction of supernovae eject our process nuclei to the interstellar medium, or that each supernova ejects only a very small amount of our processed material. The ejected material must be relatively neutron-rich, a condition which has been difficult to achieve in models, so that astrophysicists remain uneasy about their adequacy for successful OR process yields. In 2017, entirely new astronomical data about the OR process was discovered in data about the merger of two neutron stars. Using the gravitational wave data captured in G170,817 to identify the location of the merger, several teams observed and studied optical data of the merger, finding spectroscopic evidence of our process material thrown off by the merging neutron stars. The bulk of this material seems to consist of two types: hot blue masses of highly radioactive are process matter of lower mass range heavy nuclei of 140 such as strontium, and cooler red masses of higher mass number are process nuclei of 140 rich in Ac. When released from the huge internal pressure of the neutron star, these ejected expand and form seed heavy nuclei that rapidly capture free neutrons and radiate detected optical light for about a week. Such duration of luminosity would not be possible without heating by internal radioactive decay, which is provided by our process nuclei near their waiting points. Two distinct mass regions, a 140 and a 140 for the OR process yields, have been known since the first time dependent calculations of the OR process. Because of these spectroscopic features, it has been argued that such nucleosynthesis in the Milky Way has been primarily ejected from neutron-star mergers rather than from supernovae. These results offer a new possibility for clarifying 6 decades of uncertainty over the site of origin of our process nuclei. Confirming relevance to the OR process is that it is radiogenic power from radioactive decay of our process nuclei that maintains the visibility of these spun-off our process fragments. Otherwise, they would dim quickly. Such alternative sites were first seriously proposed in 1974 as decompressing neutron-star matter. It was proposed such matter is ejected from neutron stars merging with black holes in compact binaries. In 1989 and 1999, this scenario was extended to binary neutron-star mergers, a binary star system of two neutron stars that collide. After preliminary identification of these sites, the scenario was confirmed in G170,817. Current astrophysical models suggest that a single neutron-star merger event may have generated between 3 and 13 Earth masses of gold.